The central Mediterranean is one of the most interesting areas on Earth. It's an active plate margin characterized by the presence of both continental and oceanic lithosphere. Its recent tectonic history is marked by intense seismic and volcanic activity, triggered by episodes of continental collision and slab rollback that have led to the formation of mountain ranges and extensional basins. Our understanding of its structural heterogeneity and tectonic complexity requires the accurate imaging of the subsurface. Several seismic tomography models have been proposed over the last decades. However, although several authors have shown that the isotropic approximation introduces artifacts into the tomographic image, most of these previous studies neglected seismic anisotropy. But what is seismic anisotropy? Well, the simplest definition says that seismic anisotropy is the dependence of wave velocity on propagation direction. That is, a wave that is traveling through an anisotropic body will travel at different velocities depending on the direction of propagation. We have recently conducted and published on Journal of Geophysical Research Solid Earth the first teleseismic P-wave anisotropic tomography of the central Mediterranean. In this work, we presented new isotropic and anisotropic images of the upper mantle beneath the central Mediterranean area. We observed that the primary effect of including anisotropic parameters in the inversion is to reduce the magnitude of the anomalies, more significantly for low-velocity zones relative to high-velocity zones, highlighting how such features could be artifacts in purely isotropic images. For example, this effect is particularly evident for the southern France and the Adriatic Ionian slow anomalies, whose amplitude are strongly reduced in coincidence with regions of strong P-wave anisotropy as shown by the length of the black bars in the image. Then, interpreting the high-velocity zones as subducting bodies, a three-dimensional reconstruction of the lithospheric slabs beneath the central Mediterranean is derived from our preferred anisotropic velocity models. Three main segments of subducting lithosphere are identified belonging to the Eurasian, Ionian, and Adria plates. These slabs are interrupted by several slabs windows and tiers. This study presents a new three-dimensional model of the Earth's interior below the central Mediterranean. The resulting model accounts for seismic anisotropy, allowing us to also infer directions of mantle flow, thanks to the link between anisotropy and mantle deformation. We have found that the central Mediterranean is underlined by many distinct regions of lithosphere descending into the Earth's mantle, and the motion of these slabs drives regional mantle flow patterns that are largely consistent with our anisotropy observations. If you are interested in this work, don't forget to check it out.